All right, everybody. Thank you so much for being here. And I would just like to welcome everybody to the Dark Matters session of the Undergraduate Research Symposium at the University of Oregon. And today we have some very interesting student research projects to present. I'm really excited to have these students talk about their achievements. And I also wanted to just provide some housekeeping information before we get started, as I see attendees joining us. Today, we're using a Zoom webinar feature. So you can utilize the Q&A feature, which should be in the bottom of your screen. You can use that Q&A to submit questions to our student presenters. We will allow students to take questions during and after their presentations, but we will also have a general time at the end for Q&A. So if you'd like to hold your questions until the very end, that's totally fine. Each of the students will have 10 to 15 minutes to present their topic. And again, then we'll have some time afterwards for questions. This session is being recorded, so this will be available on the YouTube channel in the next couple of weeks and in perpetuity. So if you're watching in the future, hello. I'm going to turn it over to our first presenter today, who is Tyler. And Tyler is going to be presenting an affordable search for dark matter, the forward search experiment in a nutshell. Tyler, take it away.
All right, go ahead and share my screen. Oops, give me 1 second, sorry.
No worries at all. It wouldn't be a Zoom session if there weren't some technical hiccups.
Okay, can you all see that?
Yep. Awesome. And this is the slide that you want to get started?
No, it is not. Here, let me go back. Sorry. Trying to find my cursor. It's not working.
That looks like it. Fabulous. All right, Tyler, take it away. Just remember, don't forget to introduce yourself. Let us know your major, any minors you have, where you're from, and what year you are at the U of O.
Sure, yeah, so my name is Tyler Christenson. I'm a 4th year physics and max major. I have been doing research for about 2 years-ish for Dr. Eric Torrance in the high energy physics department. I've been doing work on, as you can see in the title slide, something called phasor. And I'll get into that in just a second. So I will be talking about this collaboration called phasor at the Large Hadron Collider. It's a new and upcoming particle physics experiment aimed at probing the dark matter regime. Towards the end of my talk, I'm going to get into the research that I've done specifically, but the beginning of my talk will be just about phasor because it's a new experiment, and I figure it would be good to give you guys some background into what exactly it is. So before I get started on that, though, I wanted to give you guys a bit of a breakdown on what dark matter is. So dark matter as a concept is a hypothesized solution to a problem that's perplexed scientists, physicists, you name it, for nearly a century. And the main thing that it stemmed from was galaxy rotation curves, which is pictured in the top right there. So that is showing plots of the orbital velocity of some bodies in a galaxy as a function of the distance from their galactic centers. And as you can see, as you increase the distance from the galaxy centers, they're increasing in orbital velocity. And that's not what we expect to see. We expect to see what is shown in the dotted line there, a Keplerian behavior, if you will, of what we see in a planet that's orbiting around our sun. And so it obviously doesn't follow what we expect, and that's not good. So something's missing there, and it's either we don't have a proper understanding of orbital dynamics, which isn't really likely because of all our capabilities of sending probes and telescopes and satellites to different celestial bodies. And so the other flip side of that is that there's some mass out there that we can't see, and it's causing this sort of behavior. And so what are we doing to actually study this? So dark matter has become one of the main goals of high energy physics, to no one's surprise. These things called weakly interacting massive particles, or WIMPs for short, are the main candidates. And they've been studied quite a bit in detail, but they haven't yet been observed. So that's kind of the caveat. New studies, because they haven't been observed, new studies have begun to aim to detect this sort of mediator between what we have as the standard model, protons, electrons, et cetera, and this dark sector in which these WIMPs potentially reside. And Phaser is one of these new studies, but it's unique because it's low in cost and it's pretty small compared to what your typical detectors are. And those are both really important for this study. So what is Phaser? Well, it's a new experiment at the LHC, the Large Hadron Collider, looking for long-lived particles, specifically what we're calling the dark photon. It's one of these medias. And these would be traveling from the Alice interaction point and then decaying into these positron-electron pairs in our detector that we would then be able to see and kind of trace back to that interaction point from Atlas, and potentially characterize it as the existence of one of these dark photons. And the kind of quantum mechanical process is shown there in that Feynman diagram below. So you have some light meson, say a pion is decaying into a photon and a dark photon. And then you have this dark photon doing some mixing and then converting into a standard model photon, which then decays again into these positron-electron pairs, which is the kind of thing we expect to see. But it turns out that these events, like these pions decaying into this dark photon, are really rare. So something on the order in 1 in every 10 to the 10 occurrences of a pion decay. And so that's not good. But luckily, Phaser is located in a specific way such that you get tons and tons and tons of these pions going in the direction of Phaser. So by tons and tons, I mean on the order of 10 to the 15. And so that more than makes up for this rarity of this dark photon occurrence. So about the location. So Phaser is located in a service tunnel just downstream, so about 500 meters downstream. By downstream, I mean kind of down the main beam pipe of the LHC, the main ring. That's downstream from the Atlas IP, so the interaction point of Atlas. And so what happens basically, or what we predict is going to happen, is that from the Atlas interaction point, you're going to get these large amounts of collimated just remnants or trash from the interactions from Atlas. But out of that remnants is going to be these pions, these muons, and other things like that. And so we expect to get a very high number of those from that location. So getting into Phaser now. So this is a schematic diagram of Phaser. So if anybody in here is relatively familiar with a typical detector layout, they're pretty complex. But what's cool about Phaser is that it's relatively simple. So you have, these tracking planes that are spread out throughout the detector. You have these scintillators that are spread throughout, and then you have these magnets that separate these charged particles that we would expect to see as a signal. And then towards the end, you have these caliber modules, which I'll get into in just a bit. And another thing that's really good about this detector is that it's going to be built and ready by next year. It actually already is built, but it'll be ready to collect data by next year in run 3 for the LHC. And when I say that Phaser is small, I mean really small. So pictured here in the middle is Atlas. That's like the main collaboration that the University of Oregon works with. And that's about 25 meters tall and about 40 something meters long. And you can see kind of really small down there is Phaser in the red. Now I've blown it up for you in the bottom right, so you can kind of see in a little bit more detail. kind of lined out there is a typical size of a person. And so it's definitely, by comparison, very small in the grand scheme of things, which I guess is pretty cool and makes it unique. To get some sort of real-time reference for this. So this is that service tunnel I was talking about, pictured on the left with the guy standing in front of it. That is, to the left of him, the actual phaser detector already being built. So this is in March of this year. In the last couple of months, I believe it's been finished. And so obviously that's really good. And then for a bit of reference for the location, in the bottom right of that picture, you can actually see the main ring of the LHC. So it's right there. So it's just tangent to that ring. Now, getting into a bit about the signal that we expect to see. So as I've been saying, we expect to see these oppositely charged pairs going through our detector. And specifically, we're looking for two highly energetics on the order of a TeV or so, oppositely charged particles that have a common vertex inside of this decay volume. So the decay volume being that 1.5 meter long, half a Tesla magnet. And we expect that vertex to be pointing back to the Atlas interaction point. So if you were to trace these tracks all the way back, it should be coming from around that area. And what's unique about this, so because we're looking for dark matter in this, we would not expect to see a track going through the first scintillator of our detector. So you can see that dotted red circle to the left there. Signifies that we wouldn't expect to actually see any track there because it's a dark photon and it's not really interacting with anything. We would just expect to see the spontaneous appearance of this electron-positron pair. And with that in mind, so we do have some background to this. Like I said, it's just a bunch of just stuff coming from Atlas. And so we expect to see quite a bit of muons coming through our detector, but it's not that relevant because of that unique track signal. So for muons, they would be interacting with that front veto scintillator, as we call it. And so we can just discard those straight off the bat, given that information. So delving in a bit more into this detector. So kind of the meat of this detector, what makes this actually work and how we're able to decipher tracks is through these tracking stations. So the breakdown of these is at the bottom of the screen. So what I mean by tracking station is 3 of these planes pictured in the middle, which is then comprised of 8 of these, what we call silicon strip tracking modules. So this basically just gives us some sort of spatial reference to these tracks going through our detector. And these modules are laid out all over these tracking planes in an arrangement such that they cover the whole face of the tracking plane. So we don't want any holes, obviously, because we'll miss something. And so 3 of those combines to make 1 tracking station. And then we have 3 tracking stations throughout this detector, separated apart such that they give like the optimal resolution so we can actually see the separation of them. Okay, and then the calorimeter part of our detector. So this is a bit more relevant to the kind of stuff I've studied, and so this is a good segue into that. But a bit of background about the calorimeter. So Phaser, the collaboration actually borrowed some of these electromagnetic calorimeter modules from the LHC-B experiment, which is also at the LHC. These are Shashlik type calorimeters, meaning they are arranged in layers. So they have alternating layers of lead and plastic scintillator. And specifically for these, there's 66 of those layers. And so what these calorimeters do is you have these particles that are just colliding with them at the end of our detector. They're colliding with the lead specifically. It's causing them to deposit the energy in that lead. And then the scintillators that are interweave with that lead is going to pick up that energy that's deposited. And because of the layout of this, we expect a theoretical energy resolution of about 1%, which is decent for a collaboration of this size. But this is going to be pretty limited by the amount of energy punched through the back of the calorimeter. So for pretty high energy events, so on the order of a couple TeV, we're going to get some punch through the back, and not all of that energy is actually going to be deposited in our calorimeters. And so some of it's missing, but we can account for that through some back-end studies. So like I said, this is a good segue into the research that I had done last year. So this was after last year's symposium. So I didn't get to present then, but nonetheless, this is the stuff I did last year. So this is the calorimeter face, pictured kind of in the middle of the screen with all those dots through it. What I was tasked with last year was to try and characterize the effects of these wavelength shifting fibers that pass through the face of the calorimeter and go throughout the entire length of it. And what those do is they basically collect all the light that gets passed through the scintillators and reads it out in a voltage reading, if you will. But the caveat to this is that they create dead space in the calorimeter. So these are quite literally holes through the calorimeter. And so say if a particle was to pass through one of these, it wouldn't get any energy deposited in the calorimeter, and that would affect our results. And so I was tasked with determining the actual effects of these. And a bit of reference, so you can kind of see what I'm talking about. In the bottom right picture is something that I actually managed to simulate with JONT4, which is kind of your go-getter high energy physics simulator. And so that is an instance of an actual just simulated hole through the calorimeter that I also simulated. So the actual research that I did, so with these simulations, so I have this calorimeter with holes through them, and I also made an instance of these simulations without holes so I can get some sort of comparison, some control to this. I created 3 different particle simulations. So the first of which being just a pencil beam. So that's just a line of particles. And that's going straight through one of these holes. And this was basically just as a proof of concept to make sure that my simulations actually worked and that all was good there, so that the rest of my study actually made sense. The second simulation was also a pencil beam, but this was introduced with some angle. And so we wouldn't expect particles to just go straight through the hole. On average, we would expect to have at least a fair amount of interaction with the calorimeter. And then the third simulation was kind of spread over an area in a uniform distribution of a bunch of particles. And this was supposed to best simulate what we would expect to see in the real world, sort of an interaction with the calorimeter. So here are some of the results that I actually found. So I'm only going to show you a few of these slides. I didn't want to go too far into it because it was quite a big study. But so this was the first simulation of the 3. So this was just a pencil beam straight through a hole. So the first row of plots here is showing the simulation without holes through it as the control. And as you can see, you have about 16 GeV of energy deposited, which is a good amount given the initial energy that I sent through here. And then so when you add the holes in, because this is going straight through a hole in a pencil beam, you get some average energy less than half of a GeV, and that results in a fractional energy loss of like 99%. So that proves that the holes are actually there and I can continue with the study. So then the second simulation, I just wanted to show this to you guys as well so you could actually see what the rest of it looked like. So this is, again, the top row being without holes, so a simulation without holes. And again, you can see that about 16 GeV of energy was deposited. And then because this is a pencil beam with an angle, right, it's not going straight through a hole on average. And so the bottom row, even though it has holes in the simulation, you're still getting around that 16 GeV of energy deposited, which results in a fractional energy loss of about 25% or 0.25%, sorry. And then here is a 2D plot of this. So you can see on the left, so the y-axis is the deposited energy over the incident energy. So basically the energy fraction that you get. So this is like that 16 GeV that I mentioned versus the incidence. I can't actually even see what that says, but because you guys are in the way of that. I believe that says, what does that say? Can somebody read that out to me?
Are you talking about the right-hand side of the?
The x-axis. I can't see the label.
Oh,
For some reason, you guys are blocking it on my screen.
Incident energy in GeV.
Gotcha. Yes. Okay. So this is a plot of the deposit energy over the incident energy versus the incident energy initial. So it's basically saying how much of a difference do the holes make when punched through the calorimeter. So that would be the instance of the red. So the red is a simulation with holes and the black is without holes. So you can see that as you increase this energy, you get some sort of separation between those two simulations. And that's because those jets are becoming more and more collimated as you go up in energy. And so you get more of the tracks going through more of the holes. And so less energy gets deposited in the calorimeter as a result. And okay, this is kind of a segue into what my research is now. So this is the scintillators of the detector, kind of highlighted in yellow in the top right there. So you have all of those kind of teal modules. Those are the simulator or the scintillators of the detector. And so what these do is they collect the energy deposited passing by the passing particles and convert it into visible or non-visible photons. And then with those non-visible or visible photons, you use photomultiplier tubes at the end of those scintillators to convert it into some sort of electrical output that we can actually use for data analysis. And so in the bottom right there, you can see 3 of those scintillators kind of stacked on top of each other. I think that was just for some testing purposes right there. Just for the sake of understanding what my next slide will say, so we've numbered these channels. So each of these scintillators and then the calorimeters all have a number associated with them as you for the readouts of these things. So we actually have to be able to characterize where these particles are being read out from. And so these are numbered 1 through, I believe it's 14 or 0 through 14, sorry. So what I have done here is we have worked to reconstruct the waveforms given these scintillator and calorimeter outputs. So we are, with this, so as you can see in the bottom picture there, that's an example of a reconstructed waveform. So the red dots are the raw waveform, so that's what those scintillators and the calorimeters are actually reading out. And then the blue fit is our reconstructed waveform. So what we're trying to do here is trying to best optimize these reconstructions. And specifically what I was tasked with was, or still am, is trying to determine what the best pulse time is in order to where we want to define as what a pulse is. So the start of the pulse, I guess you could say. And that's characterized visually by that red line there in the bottom left picture. And so what we're trying to do here is we're trying to compare the pulse times between different modules. So for example, in the right picture, that would be the pulse time difference between 2 adjacent veto scintillators. So 2 of the scintillators in the very front of the calorimeter. So the pulse time of one scintillator versus the pulse time of another. And so we're subtracting those 2. And so on average, we should see something around 0 nanoseconds because we shouldn't really see much of a difference if they're right next to each other, something passing in and a waveform being read out. And so what I was tasked with doing was trying to reduce the amount of width of those distributions to try and best characterize our timing for these reconstructed waveforms. And so this colorful plot here, it's kind of a lot to take in on the left. But so this is me trying to adjust a parameter of our reconstruction. So this is modifying our constant fraction discriminator, which basically tells us when to set the pulse time or the initial time for these reconstructed pulses. And so I set up a range between 0.05 and 0.6. So that's basically the ratio up to the amplitude for the peak. And so this is all plotted against the same thing. These aren't actually statistically significant. I was dealing with a really low amount of data for this, but I'm going to continue this study further with larger amounts of data and actually get some significant results. But you can kind of see the histogram shape kind of forming around 0. So this is between channels 0 and 2. So these are actually some calorimeter channels at the back of the detector. And this is comparing that timing resolution as a function of the constant fraction. So as I'm changing this constant fraction of what determining what the pulse is actually starting at, it's changing the timing resolution between the 2 channels. And so again, I was tasked with trying to minimize this difference in time between the 2 channels, given this constant fraction. And so that's kind of what I did on the right plot here. So this is plotting out a bunch of differences in readout channels. So you can see in the bottom left, the legend there compares like channel 0 to 1, 0 to 2, etc. And then it plots, basically projects what I have on the left plot there onto a 2D plot. And I'm trying to look for the minimum RMS of those plots because the minimum will tell us at which constant fraction do we get the best timing resolution for those 2 readouts. And so that's still ongoing. There's still more to be done, but I wanted to give you guys some sort of sense of what I was doing currently. But to conclude this presentation, so Phaser as a whole is a new leap in the direction of discovering the existence of dark matter. It's a relatively small collaboration. It's a small form factor, and most importantly, it's relatively cheap. The construction, like I said, is already completed, but we're still working on some commissioning with cosmic data, so just data from the atmosphere, so not actual data from the LHC, but just stuff to calibrate our detector. But it is going to be ready to collect data during Run 3 in 2022. More work still needs to be done with the backend analysis and the parameter tuning, like I'm doing right now with characterizing the timing resolution. And then the waveform construction as a result of that still needs to optimize a bit more to prepare for actual real data collection. I'd like to give some thanks to Dr. Eric Torrance and Dion Fellers for all the guidance of this research and all of the help that they've both given me. They've been such a pleasure to work with and more help than I could ever imagine. Thank you guys all for listening, and that's the end.
Awesome. Thank you so much, Tyler. Great job. And as a reminder to our attendees today, you can use that Q&A feature at the bottom of your screen to ask any questions. So if anyone has any questions for Tyler, now is a great time to put those questions in the Q&A. And I'll give you a moment, participants, to put those questions in. But Tyler, I just wanted to ask you, when you think back to your very first day when you came to the University of Oregon, did you ever think that you were going to do research on something like this?
Not at all, no. Eric Torrance honestly surprised me with such an opportunity. I was expecting just to go and do some, grunt work for some odd, research lab. But then he presented me with, hey, do you want to go and try and find dark matter with me? And I was like, you know what? Yeah, that sounds pretty cool. And so I jumped aboard, and here I am today.
Fantastic. I love that. And I feel like a lot of students at the U of O have that experience, right? They just kind of connect with someone doing research and go, gosh, well, that sounds interesting. We should probably go after that. So Tyler, what's next for you personally and professionally?
Yeah, so this research is constantly ongoing, obviously. Like I said, we hope to have this up and running by 2022. More work still needs to be done. And so I do plan to put some more time into this over the summer if I can. But professionally, I think I'm going to be going on to the master's internship program through Night Campus at the University of Oregon. So I'm not entirely sure how much time I will have to dedicate to this research, but that's where I'm headed in the next year.
Awesome. Well, congratulations. And clearly you're on to amazing things no matter what, but it does sound like you'll be quite busy for sure. So at this point, I think we are going to move on to Chester's presentation. Again, as a reminder, we will have a general Q&A session at the end, but Tyler, thanks so much. And Chester, we're going to turn it over to you. So you are welcome to share your screen and get us started. And as a reminder, don't forget to introduce yourself and let us know your major and any minors you have, where you're from, and what year you are at the U of O.
Very well, thank you, Laura, and thank you, Tyler, for the great presentation. Another example of how physicists are very, very good at naming things. So I'm just going to share my screen real quick, get to the actual beginning slide of the presentation. All right, here we go. Okay, so hello, everybody. My name is Chester Mantel. I'm a sophomore here at U of O. I'm majoring in math, physics, and Chinese. Physics-wise, I have for a long, long time been most interested in particle theory, and luckily I came to a school with a lot of great high energy theory folks. And so very recently I've been working with Professor Graham Cribbs. He is a high energy theorist here, looking into, well, I'll be getting into that in a moment, but previously I've done some work with Jim Brau and Jan Struba's group on looking at Higgs estranged decay rates at the International Linear Collider. I'm also interested in quantum computing, but that's a whole nother side topic that I don't even start to address. Otherwise, I'm from Portland. Been an Oregonian for about 5 years, but born in New York. Still have a lot of that East Coast pride. So I'm not going to wear Birkenstocks anytime soon. But aside from all of that, let's get to some physics. Okay, so as you can see, that we're going to be talking about magnetic moments of baryons in theories of strongly interacting dark matter. Now I'm going to be defining all of this, and just generally through the presentation, there'll be some key terms that I'll just highlight in red and then define those, and just ideas and key concepts I'll emphasize in blue, just for ease of readability. So we're going to start just introducing what even is the theory we are talking about, and that would be QCD, or quantum chromodynamics, the theory of particles that interact via the strong force. You've ever heard that there are three fundamental forces, one of which is the strong force. It's why atoms and nucleons can exist in the first place. QCD is mediated by gluons. They're the QCD analog of the photon for electrodynamics. Gluons are massless, they have zero charge, and they have spin of 1, which makes them bosons, and specifically gauge bosons. Now, interactions occur between particles that carry a color charge. Color is going to be a very, very important aspect here. It is the quantum chromodynamic analog for a positive or negative electrodynamic charge, except there's 3 of them. That the standard model has particles with 3 colors: red, blue, and green, and also anti-charge. Now, the name's a bit funky. When this name actually came out around the 60s, I believe, Feynman referred to his colleagues as these idiot physicists who named them. So you could say whether or not you like them. Now, only quarks and gluons have color charge. The rest are color neutral. So when we talk about QCD, we're talking about theories of quarks and gluons. One of the very, very important things that quarks can do is form these triplets called baryons. Now, if you take 2 up quarks and a down quark, you get a baryon called a proton. If you take 2 down quarks and an up quark, you get one called a neutron. So clearly, they're everywhere, and they make most of the visible matter that we see. And in QCD, color is conserved. So it has this kind of symmetry called an SU3 symmetry. Specifically, that's a special unitary symmetry of order 3, meaning it could be described by 3 by 3 unitary matrices with determinant 1. But for the sake of this talk, it just means that they have a certain, there's a certain action between elements of baryons and anything that has charge that has this 3-dimensional symmetry, so to say. And then at the bottom, I put the standard model Lagrangian for QCD. The Lagrangian is just the quantity that will then eventually lead it to the equations of motion. The left-hand term is just the phi term is describing the actual states. The Dirac operator in the middle is just expressing, essentially, it is the kinetic energy term. And on the right, there's the gluon field strength tensor, which essentially describes the potential term of all of that. And that's going to be coming up again later, so try to memorize it instantly. So dark baryons. We would like to consider the behavior of dark baryons with, instead of having 3 colors, we would have n colors. So 3 colors, you have an SU3 symmetry, and n colors, you would have an SUN symmetry. It'd be described by an n by n unitary matrix. Now, one of the main reasons for this is that we need a small parameter to expand around. If you've ever done perturbation theory, you know that you need some small parameter, and it's similar to a Taylor expansion. Now, in quantum electrodynamics, you do have that parameter, the fine structure constant, and it works quite well. But in QCD, the coupling constant G is around the energy scales we usually see about equal to 1. So that's the worst thing you could have for an expansion parameter. And you can see here this graph shows how the coupling constant runs with energy, that at low energy, it is not a good approximation at all. At high energy, it's a decent expansion parameter. But if we want to carry out any kind of meaningful calculation, we need a way to make approximations. And in that case, we need to find a new expansion parameter, which gets me into the 1 over n approximation. So if we treat the number of colors n as a parameter, we cannot treat that as a large parameter. In what we have observed, we have only 3 colors, n equals 3. But if you just imagine that it is larger than that and then take 1 over n, that's a small parameter. And that's good for expanding quantum chromodynamics in. So you can do a few things to that. One, you can actually think of having a dark sector of particles, a class of dark matter particles that actually themselves are charged under an SUN symmetry. And then from that, you can recover the n equals 3 regime. Now, if you want to do this kind of application for regular particles, you can still do this expansion and then recover the n=3 regime. Now, there have already been a lot of applications of this 1/n expansion as a phenomenological approach to standard model hadrons. And hadrons include baryons, but also mesons as well, just 2 quarks, and there's also slightly larger ones. So, for example, the pentaquark. And then the phenomenological approach that I'm talking about here is just, you could view the 1/n expansion as just a pure mathematical trick that can incidentally give you the some results that are actually physically accurate and that you could then measure. One of the important things here is that it actually simplifies calculations greatly. So having this as a phenomenological tool, it allows you to carry out calculations that you would otherwise not be able to do. Now, we can use those phenomenological results from standard model hadrons applied to dark matter. So what does the 1/n expansion tell us about dark matter phenomenology? And then another question is, what are the properties of a dark sector with an exact or approximate, that could be symmetry breaking, SUN symmetry? So for a general theory, be it dark matter or observable matter with n colors, has a few new properties. The symmetry goes from SU3 to SUN. The propagator, you go from having 8 gluons, it would be 2 to the 3, to having approximately n squared, or specifically n squared minus 1, but we're assuming n to be a large number here. You could have n squared gluons in this case. And once again, gluons are what actually mediate that interaction. And at the bottom, you can see how the Lagrangian actually changes. There's now just, you're summing over, now you're having, instead of just 3 quark colors that are indexed by C, you have n of them. This could be very important for when we actually talk about how do we then make calculations. And so instead of just kind of throwing a bunch of results at you and well, I'm gonna throw a bunch of equations, but instead of throwing a bunch of contextless equations, I'm gonna instead walk through what I think to be a really illustrative and really beautiful example of how the 1/n approximation could be applied, and how it simplifies things very nicely. So first, I need to Hooft notation. Feynman diagrams are just a way of representing the integrals that actually correspond to particle interactions and the mostly probability amplitudes of them happening. And they are very elegant diagrams, and they're everywhere in high energy theory. And in fact, Tyler presented a couple, so I appreciate the preeminent introduction. But writing Feynman diagrams into Hooft notation allows us to visualize the theory and eventually determine the counting rules, which are just the kind of ways you translate from the actual pictorial diagram to then simple integrals, or just directly going to what are the amplitudes or the relative amplitudes of any given event to happen. Now, to Hooft notation would be, instead of having, like, if you consider the image B, instead of having this squiggly line, which typically represents a gluon, you show it as 2 quark lines with one arrow going to the right and another arrow going to the left. And then you don't do anything to the quark lines, and then you could see how if that gluon interacts with the quark, and this straight line represents a quark. If you have the gluon interacting with the quark, it then becomes this kind of bottomless pit type diagram. And you could see how that would work for a triple gluon interaction or a quadruple gluon interaction, and so on. It's just a notational change, but it allows a pretty nice simplification. One more thing that's necessary, just the setup to actually get to the result, is rescale the coupling parameter that I talked about earlier, G, to G over the square root of n, and then the fields appropriately, so that you can then get a Lagrangian of this form. Now, the fields are just going to be the quarks indexed by C, and the gluon field strength tensors here. You just need to play around with them, add a factor of root n where you need to, so that you actually have this as a Lagrangian. It doesn't actually change the equations of motion. It's just a difference in the scaling, but it is very nice and a very neat mathematical idea, because it allows you to do what I think to be a pretty cool thing. That from this, you have a pretty easy way to determine the independence. That a gluon interaction, where you just have really any gluon connecting to a solid line, if you look at the Lagrangian, it would then pick up a factor of n. That there's going to be there's a new interaction term, and as you see, there's a factor of n out in front, just picks up a factor of n, and as I shown here, it looks like just a kink in and then a kink out. So graphically, it's going to look like a vertex. If you have a propagator, which is just having some or some extra gluon line in any given process, it's going to pick up a factor of 1 over n squared, or of 1 over n, and that's just a consequence from the rescaling of it. And geometrically, that's going to look like an edge. And so you can see here that you have these new gluon terms. You use these gluon terms, and it gives you when you actually have the full diagram, it gives you an extra line. And mathematically, if you take the kind of graph theoretical view on it, it looks like an edge. And then lastly, a quark or gluon loop, you get the factor of n, which is from the summation term here, that you have another n colors to actually sum over. And you could just imagine that you have some particle, you have some quark or some propagator that actually connects to one of the quark lines or gluon lines and then reconnects. It's going to look like a closed loop or a handle, so to say. So you then have the independence of a diagram. It looks like n to the power of the number of vertices minus the number of edges plus the number of handles, which is denoted as f. But vertices minus the number of edges plus the number of handles, that is called the Euler characteristic, and that is a topological invariance. That means that the actual n counting rules of any given Feynman diagram only depend on its topology, has nothing to do with really any other phenomenon that are going on. Meaning you're able to take a question which was originally saying, all right, how likely is this particle interaction, to just what is the topology and what is the kind of the very high level abstract geometric properties for this for the shape that we've drawn up. And that's very nice because it allows us a completely new and in-depth analysis of it. Now, it's very difficult to just describe it visually, so I have some, or verbally, so I have some visuals to accompany it. The top one, I think it demonstrates just how much it simplifies it, that you would otherwise be needing to count a lot of factors of n minus 1, and adding them all up. And when you especially go to higher order, you're going to be counting extremely complicated diagrams. So being able to simplify it and then just model it in terms of the topology gives a great deal of simplification. And on the bottom diagram, I just think it's very interesting. It's a very pretty way to actually illustrate what's going on. And that was from the original paper in the 80s. So this is an ancient theory, apparently, of where this all comes from. Yeah, and this can then be used and kind of carried on even further, that in the 1 over n approximation, just with the way that things scale, you then have things like quark loops, which actually get suppressed, that those handle-like properties. So if you want to carry out a calculation of first order, you can completely ignore them. And if you take n to be large or n to be infinite, they then get infinitely suppressed, and the probability of them happening goes to 0, which is really nice because when you want to calculate, well, a lot of new phenomenon or difficult or very precise ones, having that kind of suppression allows you to get answers and exact results where that would otherwise be impossible. So at this point, I hope that I've convinced you that the 1 over n approximation has some merit to it, but as of now, it's just been a mathematical trick. But how's it actually useful? For one application, which is what I've looked into recently, would be in magnetic moments. That exact theories of baryons are very difficult, and one property of those would be magnetic moments or magnetic moment transitions, which are just matrix elements of something that you could derive from Feynman diagrams and from a lot of algebra. And then what do these look like in the 1 over n approximation? Recently, and over the past about 30 years, there have been a handful of papers on this, and then you can actually derive with varying degrees of confidence and accuracy relationships between magnetic moments. Between magnetic moments. In this case, it's specifically the electric dipole moment. But what that allows you to do is now have selection rules of your matrix elements. What that means is that if you're actually trying to calculate, well, what some magnetic dipole moment is, or some transition element is, you're able to infer that based on previous results and just have a hierarchy and an ordering to what everything is supposed to look like. Having relationships between these matrix elements just in some cases is a massive simplification, and others is extremely insightful into the actual symmetries that are going on in and of itself. So on the left is just a theoretical prediction of it, and on the right, you actually have predictions of otherwise unmeasured magnetic moments. So this a 1/n expansion as an approach to just simplify calculations in QCD in general has bared fruit, as you can see right on the right, that it is able to actually simplify the calculations you would otherwise want to do, and from that you can determine, well, things that would otherwise be mathematically impossible or just unreasonably difficult, that they wouldn't get done within, I don't know, hundreds of years before more sophisticated techniques get developed. So then, question about dark matter, the most important one, that we could ask, how does dark matter behave in the 1/n approximation? One thing that we would like to do is translate the results from the 1/n baryon phenomenology to dark matter, because what I've shown you so far was all just done in the case of standard model baryons. How can we model them and then eventually recover the n=3 regime? If we can use those results for studying dark matter, we've then taken 30, 40 years of literature and then just thrown it all at a very, thrown it at dark matter, something that's very highly motivated, and that's very, very useful, because now we are able to apply a lot of them and find a lot of connections there, and then figure out what actual precise properties of dark matter would need to be. And then one thing that we've looked into more specifically is these results right here, these four. In how general of a context can they be applied? They were derived in a context, and when I say a context, I really mean a specific algebraic theory, that there's a lot of commutators and matrix elements that are assumed and that are asserted here. But can we translate this from the set of assumptions and mathematical framework that was used in this case into a theory of dark matter, and can we make that more general so that we can use these results and use the very numerical and testable results about the relationships between electric dipole moments and quadrupole moments, and then we can use that to constrain parameter space of what dark matter baryons should look like. That would be very useful, and that would be the goal. This is a bit of a new project, so I can't tell you whether or not we can yet, but maybe send me an email in a year or two and I can tell you something. And then lastly, it would be about the relic density. What are the properties of dark matter that themselves have an SUN gauge group, not just from approximating them, but let's say that there's a theory of dark matter that actually has n colors, or something that behaves like n colors. What are the properties of this? For example, what could that tell us about the dark matter that we observed, or how much of it? In the middle here, I put the dark matter relic density equation. Tyler actually introduced some of this for me, which I appreciate, that we actually are able to determine how much dark matter should exist in the universe today based on this equation. XF is it's a surrogate for time. It corresponds to when dark matter freezes out, which is when the number of degrees of freedom become essentially useless. They're no longer real degrees of freedom because it's too cold. There's not enough energy for them to actually do anything or affect the interactions anyway. G star is the number of degrees of freedom in an early universe cosmology, but it corresponds to the number of degrees of freedom that a theory of dark matter will allow. And this sigma nu corresponds to an annihilation cross-section, or the probability and frequency of dark matter essentially colliding into each other and annihilating, or dark matter annihilating with real matter. Now, what's really nice about the 1/n approximation is that it gives both a look for the symmetries of and a mathematical technique to analyze dark matter in general, but it doesn't require too specific properties as to how many degrees of freedom does it have, what's the mass of the dark matter in this theory, what are the couplings, and so you're able to come up with a lot of model and variant results, and then from that come up with various ways to constrain parameter space of these theories of dark matter. dark matter is still something that's not well understood theoretically. And so we're going to need to actually develop these mathematical devices and tools to understand what we're looking for and how we can actually probe them in the future, and at the end of the day, what it actually is. And that's all for my presentation. Thank you all for listening. Just drop any questions if you have.
Awesome. Thank you so much, Chester. Great job. And, I wanted to ask, the first thing that came to my mind was how your project has been affected by COVID and your college experience in general. So how has that impacted your research and your academic work?
If anything, it's been beneficial.
That's great.
Yeah, for the theory
linings.
research, it's kind of done nothing because, I mean, there's no such thing as a lab for theory. It's just pen and paper. There, I have my lab right behind me. And so everything could just be done online, and it's basically been a directed reading program at this point. So Zoom has not been too detrimental. Actually, it's beneficial in the sense that quarantine last year gave me way more time to work on research. The way in which I have been hurt by it is I had a fully funded trip to Taiwan that I was supposed to go to in 2 weeks. That's been canceled. That's no good. I'm gonna go to Korea instead, though. Who knows? Yeah.
Well, I'm glad that you have backup options. That's phenomenal. So knowing that you've got some brighter days ahead, we look forward to getting more and more folks back on campus. What is next for you? If you could pick your ideal research to continue or maybe pick up, what would you do next?
Well, I mean, I'm going to be continuing with this. This project is the very, very early phases. And next year I'm going to be taking quantum field theory and graduate algebra, which are kind of two of the heavy hitters in the graduate school. And that will really get me going for theory research. If you couldn't tell, I want to be a theorist, and this is the route to get there, hopefully. But I also am going to be joining a lab for quantum computing next term, and I might do some math research over the summer if you want to talk about approximately commutating algebras.
Excellent. Well, we fully expect to see you back here next year in whatever context it may be, Zoom or in person or both. But yeah, thank you so much, Chester. And we're going to now turn it over to Laura, who is our last presenter of the day. And Laura, as a reminder, don't forget to introduce yourself and go ahead and share your screen now.
Okay, thank you. I'm Laura. I'm in my 3rd year here at the U of O. I'm a physics major. I'm from Portland. I guess that's it.
I think that covers it.
Let me get my slides up. Okay, does that work well? Can you see it?
Looks great. Go ahead.
Okay, good. I'm just gonna rearrange some windows from Zoom and then, okay, I can get started. Can I, oh, there we go. In our project, we're studying the production of long-lived dark photons at the ILC, which is the International Linear Collider. And we're going to be, in our project, we hope to provide a benchmark for long-lived particle studies at the ILC. So an outline for this talk, I'm going to talk a little bit about dark matter and then dark photons, and then the ILC itself. And then our study, our methods, and some of the properties of dark photons and its decay products. And then some initial results. We're still in the early days of the study and the outlook for what the future is. So as we've heard about dark matter in the past couple of talks, so dark matter, there's still a lot in the universe that we can tell is there by looking at the effects that it has on ordinary matter that we can see, but we can't see it directly, and we call this dark matter. We can see its effects in rotation of galaxies. We can see it in the expansion of the universe. And here is a pretty famous example of a way that we can see that dark matter should be there, is the bullet cluster, whose center of mass doesn't match up with where it should be for the amount of matter that we see. And we can see from gravitational lensing that there should be way more stuff there that we can't actually see. So if we were to look at the amount of ordinary matter there is in the universe, things like muons and Higgs bosons, which look like this, the dark matter would outweigh it about 6 to 1. And it's entirely possible that dark matter consists of particles, much like ordinary matter does. So we're doing a search for a particular type of dark matter particle called the dark photon. And I got a Feynman diagram for you. So dark photons would be sort of the dark matter analog to the standard model photon. They would be force carriers, just like the photon is in the standard model. And they would be the lightest particle in the family of dark matter particles, which gives it this unique ability to potentially interact with our ordinary particles, the standard model of ordinary particles. So that way we might be able to actually see some of its effects from it interacting with the stuff that we can see. Here on the side, we can see this is a plot from a model that we're using by the theorist David Curtin and his collaborators. And this shows the dark photon mass. This parameter epsilon here, you don't have to worry too much about. It basically tells you how much the dark photons are interacting with ordinary matter. But this graph gives us a way to look at long-lived dark photons because it shows the connection between the mass, this mixing epsilon that we can control, and the lifetime. So for example, if we decide that we want to look for 10 GeV mass dark photons, we can pick a certain epsilon here, like 10 to the minus 6, that matches up with that mass, and it'll give us a certain lifetime. Here, this gives us 10 to the minus 3, which is gives you a measure of sort of the distance that it'll go. And here, I'll get the video going. I hope this isn't too distracting. It's just too much fun to not include it. The International Linear Collider is a proposed collider, so it doesn't actually exist yet. That would be, like the name says, a linear collider, as opposed to like the LHC at CERN, which is a circular collider. And also, unlike the LHC, which collides protons and some other stuff, the ILC would be an electron-positron collider. And this doesn't get you quite as high of an energy as the LHC does, but what it gets you is a really clean environment. So the LHC collisions can be really messy with a lot of showers of different particles, and the ILC should be really clean. Also, the ILC is predicted to be a Higgs factory, which is a really exciting name, and it means that it's predicted to produce a lot of Higgs bosons. So looking for dark photons at the ILC, there's some good motivation for why to use the ILC for this. It's got a clean environment, which is great for studying weakly interacting particles that have long lifetimes, like the dark photon. It has the high Higgs production rate that I mentioned. In particular, this process here called Higgs-Strahlung is shown here on the plot over here. We'll be looking at this energy, the ILC tuned to this energy, which is right at the peak of this particular production of Higgs bosons. And this is what we're using in our model, assuming that's how we're getting our Higgs that then get the dark photons. So this is, all in all, it should be ideal for studying long-lived particles and specifically the dark photons, because all of these factors are coming together to make it a pretty good environment. There have been some similar studies at other experiments. This study in particular, I want to highlight because it's where we're getting our model. We're just tweaking it a little bit to give the dark photons a longer life. This one was a study done by David Curtin and his collaborators at the high luminosity LHC, which is some proposed upgrades to the LHC. And it studied dark photons that don't have a long lifetime, but by this production mechanism. There's also been other studies here that I've listed at other future potential colliders, looking at different types of exotic Higgs decays, some to long-lived particles, some of them to this fun thing on the side over here called Higgs to Invisible, which is a great name. And this picture on the right here is just from this study by David Curtin, showing some of his results for the sensitivity to dark photon production based on some different variables. So for our study, we'd like to determine the ILC's sensitivity to dark photons. And also, we want to increase the overall interest in using the ILC to study long-lived particles in the long-lived particle community. And remember, it's a detector that hasn't been built yet. So we also want to establish its viability for other long-lived particle studies and just get a benchmark for how good it's going to be for doing these sorts of studies. So you may start to wonder, if we're looking for theoretical particles at a detector that doesn't exist yet, how do you even start doing that? What we use are these really high-level simulations that are made by these 3 different programs here, called MadGraph, Pythia, and Delphis. MadGraph, you start out with that, and that defines your signature. So like, for instance, electron and positron, to Z and a Higgs, to 2 dark photons and whatever. And then it generates some simulated events based on that signature and those processes. And then it describes the properties of the particles in the event, and it gives them things like their momentum and their position. Then we have this special program called Pythia, which just deals with the quarks and the gluons in the event, looking at the QCD of that. And because that's quite a complicated process, we need a dedicated program for that. And then finally, we have something called Delphis, which simulates what would happen if the particles actually go through the detector. So this is where we give it the information of, we're using the ILC in this detector, and it shows us what it would look like if it actually went through the detector. So we can, once we run these event generators or the simulators, we can look at some of the properties of the particles that it generated. Here's the dark photon decay products. Oh, I don't think I mentioned the dark photon is decaying to an electron and a positron, or a muon and an anti-muon. We're just looking at those decays now, but it can decay also to quarks. We'll add those in later in our studies, but for now we're just starting with decaying to electrons or muons. But this is looking at the decay products and just some properties of them. Here, this is their distribution in the detector with the polar angle theta. And we can see it's centered around a central theta value. This is in terms of radians. And then over here, we can see the momentum of the decay products. And I wanted to show also this here is the momentum of just looking at the dark photons themselves. And we can see that this is sort of centered around what this is centered is about half of this, which is what we would expect because it decays to 2. So they each are going to have about half of the momentum of the first one. And you can see here there are 2 lines. The black line is the truth level and the blue line is Delphis. And these are basically just different stages of the reconstruction process, where Delphis is that program that shows you what happens when it goes through the detector itself. And this is the truth level is just before we even worry about it going through the detector, just looking at it as it is. We can look at the invariant mass of the particles here, and the blue line, because that's Delphis again, because we're looking at the particles that have gone through the detector, this is a lot closer to what we would see in an actual detector. And the way that we get this is by reconstructing back from those electrons and muons and adding up as pairs their masses until we can see the distributions of what they came from. So here, if we add up the masses of some electrons that came from a dark photon, you'll get a peak around the dark photon mass, which is this peak here. It's for 10 GeV dark photons. And this peak here is the Z bosons, which it's much smaller in the reconstructed, but that's just because Z bosons tend to decay mostly to quarks. So this is just looking at electrons and muons, so there's not going to be so many of those from Z boson decays. And we can also directly see that the dark photons that we've made with our samples have longer lifetimes by looking at some of their decay distances. Here I've included, we have a total of 4 samples that we're using. And here I've included the shortest decaying one and the longest one, and a summary of the distances in the table here. And so you can see we have quite a range. And that all goes back to that one graph I showed you with all of the lines. And how we can pick different lifetimes based on changing this epsilon number and the mass of the dark photon. So we want to try to determine how the sensitivity for finding these things in the detector. So the way that we do that is we define different regions, meaning different parts of the detector where we want it to decay. And we can also define some restrictions on the decay products, say things like it has to have a momentum greater than this or whatever. And then that gives us a way of narrowing down our search. Then with those different regions, we can find out how many particles fit that category. And the number of total events that we've created, we can use that to find out the fraction of events that we would expect to be able to find a dark photon. And that gives us an acceptance value. And then we can use those expectations, the fractions that we get from there, as well as some properties of the event and of the detector to find different limits on the sensitivity. So for example, here I have a schematic of the SID, which is the detector that we're looking at the ILC. And we can say, for instance, we want them to decay before here, and we want like a minimum momentum of like 2 GeV or something like that. And we can program that in and then run through and see how many dark photons fit that category, and figure out the percentage of events where you're going to have something here with those restrictions. And I just included our results for the samples that we have here. But the actual numbers aren't really as important to remember for now. And then, as I mentioned in the last point here, we can use these percentages that you get from this process to get some limits on the sensitivity. Here, we're going to be limiting the sensitivity based on something called the branching ratio, which is just the fraction of particles that that are decaying a particular way. And here, we're finding the minimum branching ratio of Higgs to dark photons for us to be able to detect the dark photons. So basically that just means the smallest fraction of Higgs that can decay to dark photons for us to still be able to find dark photons, like how rare it can be. And these are the branching ratios that I calculated here for our different samples. And I've put them on the plot over here from David Curtin's paper for the high luminosity LHC, just to show that we're in sort of the same general area, and that these results seem reasonable for now. So our outlook is that the project looks promising. The ILC should be pretty good for studying long-lived particles, and we're excited to start looking at different properties and different ways of finding out just how good it might be or at finding long-lived particles. We want to study these acceptances and sensitivities a bit further and more systematically and add in some different decay types. So as I mentioned, we're just looking at dark photons that decay to electrons and muons, but they can also decay to quarks. And if we add that in, that will actually decrease, if I go back up here, decrease these minimums, which is what we want, because we want a smaller minimum that we can look up to. We want to be able to look for even rarer and rarer things. And adding in those different decay types should help with those numbers. We also want to use some more advanced types of reconstructions and simulations, in particular a full simulation. And that will give us the ability to study backgrounds, which are other things going on in the event that could be mistaken for the signal, and determine what potential backgrounds there could be, and how important they are in the study. And I just wanted to acknowledge the fact that I was supported over the summer by the VPRI Fellowship to work on this project, and that where we got our model and where we got the schematics for the detector and the card which we used to generate these events in Delphi's by Chris Potter. And a big thank you to my advisor, Laura Janti, and to Chris Potter for all of their help with this whole project. Thank you.
Fantastic. Thank you so much, Laura. And, you know, this really has been such a fascinating trip through our physics department through the lens of 3 of our outstanding students doing research. And Laura, I wonder, you know, looking back, is there one thing that maybe you would change about how you approached your research or anything that maybe you wish had gone a little bit differently?
Yeah, maybe asking more questions or asking questions earlier because early on in my research, I feel like there were some times when I spent longer working on trying to figure out a solution to something when I could have just asked someone with a lot more expertise than me who just knows the answer. And that gives you good skills of being able to research and find your own answers, but sometimes it's really useful just to ask earlier.
Absolutely. And so what is next for you? What are you hoping to do in the future? I mean, I'm sure you're not just going to drop this, right?
No, yeah. I'm going to be going to grad school after I graduate here, and I don't really know where I'm going to go yet. And I'd like to keep studying this sort of thing. The experimental particle physics is really fun for me, especially long-lived particles and Higgs physics. Those are really interesting subjects to me, so I want to keep doing this.
Fantastic. Well, as I reminded the students in a session earlier today, this is being recorded, so you may get emails across the next few weeks after this gets put up on YouTube. Certainly, it is an ever continuing conversation. And so at this time, I would like to invite any questions from our attendees. Again, you can use that Q&A feature. This is a great time to ask questions of any of our presenters today, as we have just a few more minutes left with them. So again, if you have any questions for our attendees, feel free to drop those in the Q&A feature. I think I've got a quick question for each of our attendees, and just if you could use one word to describe why you chose physics, what would that word be? What word would you use to describe why physics was the right decision for you? So I'll just start in the order that we presented in. So Tyler, why don't you go first? Why physics?
I always wanted to be part of the future, I guess. I wanted to be part of something exciting and innovative. And I felt like because physics is such a fundamental thing and part of life, that it was the best way to go. And I guess to that point, I had a really inspirational high school physics teacher that really spoke to me as a student and really inspired me to go into the physics major, because I had really no idea before, I guess, my senior year of high school what I wanted to do in college. And that definitely set me on my way.
Awesome, thank you. And Chester?
Philosophy with math. That's 3, I'm sorry.
That's okay. It's a combination thereof. You just were intrigued?
Once I got into philosophy, I really got into physics, and I like doing math, and so therein lies the intersection.
Absolutely, makes perfect sense to me. And Laura, how about you? Why physics?
Like one word would just be fun, because it really is fun. I mean, I'm studying dark photons, like even just the name of it is fun. But the actual process is really rewarding, and yeah, so I'm sticking with fun.
Good. Well, that's what we like to hear. And, I'm sure all of your advisors would be very happy to hear that you still find fun in this. And that is so important, right? At the end of the day, hopefully students pick a major and pick a research project because it is fun and it is exciting and it is something that will take you on to your next big thing, whatever that is. And I feel confident that all of you will do some amazing next big things. So again, any questions for our student presenters, you can put those in the Q&A, but otherwise we will go ahead and wrap up a little bit early this evening. But thank you so much, attendees, for being here. Thank you to our student presenters, and thanks for joining us. We hope that this will be in person next year, but no matter how you join us, we look forward to connecting with you again someday soon. So stick around if you've got any questions, but otherwise, this does conclude our session, and I will stop our recording now. Are we good to stop the recording, Kenyon?
I think so. I'll go ahead and do that.
How else are the students in Japan gonna see our wonderful, insightful conversation?
Absolutely.